Greetings. Thank you for joining us today. This is the fourth in a series of webinars provided by SRE, or Sulfur Recovery Engineering. Today we're going to talk and learn a little bit about how we can best manage SRU turndown conditions. My name is Ryan McLennan. I'm a lead process engineer with Sulfur Recovery Engineering, and on our first page here, my email is provided. At any time, if you have any questions and or concerns with anything related to amine unit, gas treating, and sulfur recovery, don't hesitate to fire me an email. On your dashboard for the webinar, there are functions such that you can send me over a chat message or ask a formal question. I highly recommend that you do. There are no guarantees that I'll answer them during the webinar, but for sure I will tackle everything at the conclusion of the webinar. We should begin. To start, before we start talking about the challenges associated with turndown, it's important to review the specific reaction that's taking place in the sulfur recovery unit, specifically the Claus reaction. The Claus reaction is a gas phase equilibrium limited reaction where we react 2 molecules of H2S plus 1 molecule of SO2. We're able to make sulfur vapor, and we also produce water. So it's important to remember that this reaction itself takes place in the gas phase, gaseous reactants, gaseous products, and the reaction itself is equilibrium limited, which is very, very important. So depending on what we do or how we're operating, we may be able to influence that reaction further to the right or to the products, or negatively back to the left. So we wouldn't get very good conversion. Basically, if you remember some of our schooling, for me that was a while ago, but with respect to an equilibrium limited reaction, we can promote conversion. So conversion here is defined as being able to take H2S and generate our sulfur product. We can promote conversion or push that Claus reaction far to the right by increasing the partial pressure of H2S and SO2 in the system. It makes sense. More reactants, in theory, more products. What is very important, and really the focus today in terms of managing turndowns, is that it's not an ideal situation because overall the SRU's conversion potential is directly proportional to sulfur loading. And before we move over to the next slide and start focusing on some of these challenges, the first point mentioned that, with respect to the equilibrium limited Claus reaction in this case, we can only approach 100% conversion. And what I mean by that is, due to equilibrium, no matter what we do, we will never be able to achieve 100% conversion of H2S to sulfur. You see on the plot to the right that we never do quite reach 100%, and that is due to the equilibrium control in our process. We can get pretty close, but not to 100. SRU Turndown. Locally to SRE, we're located in Calgary, Alberta, Canada. So we're focusing here on northwestern Canada. We have a lot of natural gas, and many of our clients and gas processors are working to manage declining H2S content. And why is the overall H2S content to our SRUs declining? Well, overall, there's a drop in the amount of sour gas wells and or an increase in shale sweet gas production. What's important, I mentioned on the previous slide that overall, the SRU's overall conversion potential is directly proportional to how much sulfur is being processed in the plant. So SRU sulfur loading, so how much sulfur is being fed to the SRU is really a function of overall H2S composition that can be enhanced perhaps with optimized gas treating, but also feed flows. The combination of a flow and a composition yields, for example, an inlet tonnage rate. So for example, my SRU would process X tons of sulfur per day. In the United States, quite similar. Prevalence of both shale gas and sweet crudes has enhanced profit margins. It is easier to process shale gas and sweet crudes versus sour. But again, this leads to similar challenges with respect to the SRU. We like to have a high inlet tonnage rate, a lot of sulfur to process. The challenge: how do we maintain required sulfur recovery levels? Emissions requirements and expectations are only becoming more stringent worldwide. As I make mention in this comment, the regulator is very unlikely to cut us any breaks. Thus, we need to understand how to best manage SRU turndown conditions if that's what we're faced with, or if that's what we are projecting to have to deal with in the future. Quick schematic here of a conventional SRU. The focus today, and you'll see as we move forward, is that we're going to start at the front end with our upstream units or feed streams to the SRU and talk about the type of things that we could look at or do to enhance the performance potential of our SRU that's experiencing turndown conditions due to a drop-off in H2S quality and or overall flow. You see at the front, we mix our feed streams, amine acid gas. If we're dealing with a refinery, most refineries also process an additional feed stream, our sour water acid gas. We mix those streams and burn them with an appropriate amount of air, such that everywhere downstream in our process, we are able to react 2 molecules of H2S and 1 molecule of SO2. That's that 2-to-1 ratio that's so important from a SRU performance potential perspective. Combustion air control is one of those important parameters with respect to being able to optimize operations in our SRU. We move down the line into a series of condensers. Again, the Claus reaction itself is gas phase, so the sulfur vapor that we do produce across the reaction furnace and further downstream across our reactors, we need to condense that out to obtain our product here in the sulfur pit. This generic example is a 3-stage SRU where we have 3 catalytic converters. Why do we have 3 catalytic converters? Because, again, the reaction itself is equilibrium limited. After each converter or reaction step, if we remove sulfur vapor, we're removing the product such that when we move to the next catalytic stage, we're resetting up the opportunity to move that equilibrium limited reaction to the right because we've removed the product. So we're more favorable to move to the right. And we're able to enhance that reaction if our operations are on ratio, such that we're adding an appropriate amount of air in the front end to have that 2-to-1 ratio of H2S to SO2 everywhere in our process. As I mentioned, we'll start with some upstream considerations. So essentially, even before anything reaches the SRU. First thing we'll deal with is the potential to enrich the acid gas coming to the SRU. Just a few points. There is capital input or capital required because acid gas enrichment requires a dedicated contactor and regenerator. think of this as an additional amine or gas treating step. We're trying to maximize CO2 slip and minimize H2S leak. We want to absorb the H2S and we don't want to absorb the CO2 into our amine solution. As a result, for this enhanced performance, if you would, things like tertiary amines or sterically hindered amines are required for this application. We want to maximize the H2S content in the feed streams coming to the SRU. As a result, we want to minimize the amount of CO2 present in those streams. At the reaction furnace, we're trying to have a burn or a fire. We don't want to be adding CO2. There are a lot of reports of these units there being unrealistic expectations. In my experience and research, there appears that there are less than 30 of these units in operation today worldwide. They're tricky units. The absorption, it's mass transfer controlled, so the absorption of the acid gases, CO2 and H2S into the amine. There are lots of discussions about the internal tower design, which is so very important if we have a mass transfer limited system. Also, severe duty and corrosion. It's a severe duty process because of the corrosion potential, because we're dealing with acid gases, CO2 and H2S. You see the picture on the right. Here's corrosion at its finest. But the benefits of amine of acid gas enrichment is that we increase the partial pressure of H2S and as a result SO2 in our system because we are maximizing our CO2 slip and generating a stream that is more rich in H2S. Other factors, because we have less CO2, there's less potential to form COS across the reaction furnace. In general, CO2 plus H2S can yield COS, carbonyl sulfide. Hydrocarbons can also react with H2S and generate CS2, carbon disulfide, across the reaction furnace. As you can imagine, across the reaction furnace, there are unlimited number of side reactions that can take place, but in terms of generating our final product, sulfur, there are only two sulfur-bearing species that will directly react to generate sulfur, and that's H2S and SO2. So we would like to minimize the formation of both COS and CS2. And finally, with acid gas enrichment, it's another opportunity to slip or remove higher hydrocarbons and also the BTEX components in the application. And it's a low pressure application versus the typically higher pressure regular amine or gas treating unit that you would have. The BTEX components include benzene, toluene, ethylbenzene, or xylene. Essentially, we like to minimize their composition in our feed streams because if they're not destroyed in the reaction furnace, they will poison our Claus catalyst downstream. Another option, oxygen enrichment. Typically for turn down conditions, so a decline in H2S content and or feed flows, yielding overall less tons per day being processed in the SRU than we used to. The important thing to realize with oxygen enrichment is that it is most commonly employed to handle a capacity increase. So not so much a decrease, but actually an increase. Things to consider about oxygen is that, is this enriched oxygen stream going to be delivered to the SRU, so made somewhere else, or is it going to be generated in the refinery? Or gas plant. There's obviously a cost associated with with purifying air, essentially. Estimations at approximately 10 to 20% of the money or capital required to build a brand new SRU. It is a continuous process, so there is a continuous cost associated with generating a stream that is richer in oxygen relative to air. Also, once we start working up to higher levels of enriched oxygen streams, a special burner, a special main burner for the SRU is required for safe handling. And once we start getting north of 30% oxygen, we need to spend that extra capital and get a special burner. Oxygen enrichment, we've seen everything from, we have approximately 21% O2 in air. I've seen a plant with only about 27% oxygen, and you can work all the way up to 100% oxygen. Now, I did mention that oxygen enrichment is most commonly employed to handle SRU capacity increases. Oxygen enrichment will work to also increase the partial pressure of H2S and, as a result, SO2 in our system, because the more oxygen that we introduce, or the more of a purified airstream, if you would, we are able to remove portion of that bulky nitrogen that does nothing for us but steals heat. What's important to remember here is that relative to air, this enriched oxygen stream, which has less nitrogen in it, what we've done now is we've essentially had a further reduction in overall mass flow through the system. And that is what turndown is. Definitely being able to burn something with a stream richer in oxygen, we're able to increase our overall reaction furnace or RF temperature. And what's important to note is that temperature excursions are common with oxygen enrichment. In general, the max allowable operating temperature in our RF is about 2800 F. But the important thing with oxygen enrichment is that, yes, it will definitely work to increase our RF temperature. And we're going to come to the picture again, but on one of my very first slides, there is a plot of temperature across the different units in the SRU as a function of conversion. That's where I was showing, because the reaction itself is equilibrium limited, we can never get to 100%. We can never get to 100% conversion of H2S to sulfur. To the right of that diagram, the more temperature that we can achieve across our reaction furnace, the more initial sulfur conversion that we will experience. As a result, we do need more temperature, and oxygen enrichment can help with that. However, I did mention that oxygen enrichment is commonly employed to handle capacity increases, the ability to process more acid gas because we've removed a lot of nitrogen relative to regular processing with air. If we remove nitrogen because of oxygen enrichment, we have less mass flow through the system, and we're assuming that we already had a reduction in overall mass flow through the system because we're dealing with turndown situations. The bottom line in the picture on the right shows a burnt burner tip. Because of excessive temperatures due to employing oxygen enrichment and not having enough not having enough pressure in the system and or mass flow to push that flame in our reaction furnace far enough out from our burner tip. A very common problem that we see out in the field. But again, pros and cons to everything. Feed stream preheats. Quite easy. And here's the diagram I was talking about. The figure, you'll see to the right, our thermal section, our reaction furnace. We can have upwards of 70 to 75% initial sulfur conversion across our reaction furnace if we're able to achieve higher temperatures in our furnace, for example, 24,2500 F. We can get there with oxygen enrichment. We also can work to get more to those levels if we're able to preheat our feed streams. We're able to preheat each feed stream in the SRU, including combustion air. A step change in approach temperature to the reaction furnace. Achievable equilibrium temperatures drive initial sulfur conversion and contaminant destruction. I did mention earlier some of the contaminants present in our acid gas streams, like the BTEX components. Field testing has shown that there are specific temperatures that we would like to achieve to be able to best promote the complete destruction of some of these components like the BTEX. If we were able to increase our feed streams temperatures to say a difference of 200 degrees Fahrenheit, well, that's essentially a step change. We're coming in 200 degrees Fahrenheit hotter. In theory, for the same feeds, the same compositions, the same burn, we should be able to achieve a reaction furnace temperature that is approximately 200 degrees Fahrenheit higher than where we typically would operate. Moving a little further up and closer to our SRU front-end considerations, co-firing with fuel gas. This is going to help us get that temperature, which we've seen in that plot, that will enhance our initial sulfur conversion. And you can imagine, from an overall sulfur conversion and recovery perspective, the more work that we can do up front, the better it will be for our process and the better it will be for our downstream reactors to reduce the load just a little bit. Co-firing with fuel gas is by far the most popular retrofit or change to be made when dealing with turn-down conditions. We're able to enhance the flame stability in our reaction furnace or main burner. Of note, there seems to be issues that start developing with flame stability once we start dropping below 40 to 45% H2S. Obviously, the overall burn strategy for our unit would change if we're also adding fuel gas to the front end of our reaction furnace. In general, for a fuel gas stream that's 100% methane, the burn stoic is approximately 9 parts of air per 1 part of fuel gas. So we would have to look at the algorithm for how much air we're introducing to the reaction furnace if we're also going to supplement a little fuel gas in the front. We're able to easily achieve high RF temperatures. We saw on that plot that with more temperature, we're able to have more initial conversion of H2S to sulfur across the reaction furnace. I briefly discussed some of these temperatures. We need to achieve certain temperatures to best promote the destruction of contaminants that are present in our feed streams. At least 1900 F to best promote the complete destruction of the BTEX components. If they're not, they could potentially poison the downstream Claus catalyst. If we're at a refinery, the sour water acid gas feed stream typically contains equal parts of water, ammonia, and H2S, so 1/3 water, 1/3 ammonia, 1/3 H2S. We need a little more temperature to best destroy, to have the ability to best promote the complete destruction of ammonia. If not destroyed across the reaction furnace, ammonia salts can begin to precipitate out as we get cooler in our process. Specifically in our final condenser, that could decrease overall mass transfer in our condenser, and that will impact overall sulfur recovery. Co-firing with fuel gas increases the overall mass flow in our system, but it reduces the partial pressure of H2S and SO2 in the system. Co-firing with fuel gas helps us with our temperature, but overall it dilutes the system. methane plus oxygen yields, for a perfect burn, CO2 and water. We're generating water. One of the problems here is that the equilibrium limited Claus reaction also produces water. Back to school and thinking about equilibrium, we're adding water. Water is also a product in the reaction. We're worried about the Claus reaction. That does not help the overall conversion potential of the SRU. However, there are benefits because we can have so much more initial conversion across our reaction furnace if we're able to have more temperature, and we're able to do that with co-firing. Everything overall, there's pros and cons, but a lot of this has to do with balancing objectives and what do I need? What level of sulfur recovery or emissions do we require, and how are we going to get there? As a result, with co-firing with fuel gas, there will be a slight reduction in the overall recovery level of my SRU compared to typical or normal or past operations. Again, methane plus oxygen yields water and CO2. Overall, we will have a higher proportion of CO2 in our system, and we will have more CO2 emissions out our incinerator stack. We must have titanium catalyst in our first reactor if we're going to be co-firing with fuel gas. I did mention earlier a side reaction in the reaction furnace where hydrocarbons plus H2S can yield CS2 or carbon disulfide. This is sulfur tied up in a form that is not H2S or SO2, and it's those two components that react together at a 2-to-1 ratio to generate our final product, sulfur. Just a comment here is that, everything that we've talked about so far, it seems like in order to best manage SRU turndown conditions, we are going to have to accept some type of increased operating costs or requirements or capital to ensure environmental compliance. Co-firing with fuel gas, sometimes we get good rates and buy fuel gas from the city or town. If we're operating in a gas plant in the middle of nowhere, for example, we are going to have to co-fire with our final product, natural gas. Unfortunately, there's pros and cons to every to all options, and for that result, no one SRU or facility is the same. Main burner, high versus a low efficiency main burner at our reaction furnace. The picture to the right is not the best, but up here in A, what you'll see is a flame, and if you compare it to the flame in B, which is the flame off a CFD modeling in for a high efficiency main burner, you see a more stable and tighter flame, and that's representative of a high efficiency main burner. A lot of facilities are changing over to high efficiency main burners. All pieces of equipment have an expiry date, and we are seeing a lot of people moving over to high efficiency main burners. What's important here is that recently in the Middle East, at a Middle East job, we observed a difference of 200 degrees Fahrenheit RF temperature for similar SRUs with exactly the same feed streams. And the difference was that we had a newer SRU on site that had a high efficiency main burner, And also, and the other SRU was very old. It was from, well, not very old compared to some facilities, but it was from the 1980s when it was built, and it had a low efficiency main burner. So just with an enhancement, if you would, in the design of the high efficiency main burner, we were able to achieve a temperature change in our favor of about 200 degrees Fahrenheit when comparing a high to low efficiency main burner. Claus condensers. High turndown. High turndown, low flows compared to normal or design can lead to a low gas velocity through our condenser or condensing tubes. We call this sulfur fogging. Typically at the outlet of a condenser, so here we're taking our sulfur vapor product, we are condensing it in the tubes, along the tubes, producing liquid sulfur. You know, there is a difference between a sulfur conversion number and a sulfur recovery number, because no matter, again, what we do, we're never going to have 100% efficiency in a Claus condenser. But it is important to ensure to best promote 100% sulfur recovery in our condensers that the velocity of our process gas through our condenser is aligned with best practices. There is a minimum acceptable process gas mass velocity of 2.5 pounds per second per foot squared, an extreme lower limit of 2. In the condition of very low gas flows or high turndown, we can be so slow through a condenser tube that our heat transfer is so very good, such that instead of condensing on our sulfur tubes, we're actually forming very tiny and fine sulfur droplets midstream, such that these droplets can carry right out of the Claus condenser. Now, and headed up towards the next catalytic stage. At the outlet of each condenser, we should have a mesh pad that should help to work and knock down some of these very fine droplets, but at times they are just too fine and they're able to escape the mesh pad. And you see in the bottom picture, a nice picture of a mesh pad here, but sometimes these droplets are just so fine that they're able to not be knocked down, and they're carried over to the next catalytic stage as sulfur. They get reheated, sulfur vapor. Again, that's a product in the Claus reaction scheme. That is not favorable in terms of pushing the overall Claus reaction to the right or to the product. In terms of a capacity increase, we could have the opposite happen. We could be traveling so fast in our condenser tubes, such a high velocity that we're actually pushing liquid sulfur up and out of the condenser instead of down and towards a sulfur pit. What's important is that we have an up-to-date SRU capacity evaluation such that we can determine where our process gas mass velocities are in our Claus condensers, such that we can fine-tune operations to ensure that we're able to best promote sulfur recovery in our system. The importance here is to get updated flows in everywhere in our process. We would work with our client with equipment drawings such that we can calculate process gas mass velocities. It's a function of cross-sectional area and tube number. Sometimes in very extreme cases where the process gas mass velocity through our tubes is so very low, sometimes at next available opportunity. At a turndown, for example, teams will go in and block off a designated number of tubes such that upon restartup of the SRU, we will have a higher process gas mass velocity through our tubes. Claus converters. The Claus reaction takes place over either aluminum or titanium catalyst in general. It is very important to maximize the available amount of surface area for the reaction to take place. In the conditions of SRU turndown, primarily due to reduced feed flows, we could have channeling that could occur in our reactor. Field testing has shown that channeling can lead to apparent catalyst deactivation. Reduced catalyst runs. We are not using our entire bed of catalyst. As a result, the lifespan, if you would, of that catalyst or investment will be reduced. And again, ineffective use of investment, i.e. if we had titanium catalyst in place. Titanium catalyst is more effective at the rehydrolysis of COS and CS2 back to H2S in the first reactor compared to alumina catalyst. And as you can imagine, as a result, titanium catalyst costs more money. Full titanium catalyst is approximately 10 to 14 times more expensive than our typical generic aluminum catalyst. Things like channeling. It's important to verify our flow distribution strategy through the catalytic converter, inlet nozzles, and distributor plates. To prevent channeling, if you would, do we need to increase the mass flow in our system to have a better distribution? We could do that by co-firing with fuel gas. The picture on the right is a recent example from a field testing job just in the past couple of months that I was out on. And this is an excellent example of channeling that's occurring primarily due to low flows through our SRU. This is the first reactor. We see an inlet temperature of 442 F. We have a series of thermocouples for temperature measurements at different levels or depths in our bed. We're coming in at 442. Our top level were 576 and 528. We have an increase in temperature because another product in the Claus reaction is heat. The reaction itself is exothermic. Thus, if we have reaction occurring, we will be also generating heat or temperature. So you already see a discrepancy here, and I know that thermocouples are not perfect, but you see a discrepancy here, 576 versus 528. Then we move down to the middle, and we apparently have more Claus reaction taking place where we move up to 598. And as we move further down, we can be either 538 or 588. This particular facility, due to channeling, the flow pattern through this bed is actually from top left to bottom right. Similar for the second reactor, but actually we're moving from the top right to the bottom left due to channeling. As a result, this particular facility will have a reduced overall catalyst run or lifespan. They will have to change their catalyst out more frequently, and when they do change their catalyst out without being able to do anything with the inlet nozzles or distribution pattern to enhance flow, they will be replacing a lot of catalyst that has not been utilized at all. Claus converter performance. It's important that we maximize overall conversion potential, the Claus reaction, by way of best practice operations. We want to operate our reactors at temperatures that are 10 to 20 degrees Fahrenheit above their bed-specific dew point temperature. We see in the diagram on the bottom to the left, the catalytic section. We see, as we follow the plot, on the x-axis we have temperature, and on the y-axis we have conversion. We see that as we reduce temperature, we are able to enhance our overall conversion potential. And again, we're able to maximize conversion if we're able to operate our reactors at 10 to 20 degrees Fahrenheit above their bed-specific dew point temperature. Given the partial pressure of H2S, SO2, sulfur, temperature, different factors going into each reactor, there will be a bed-specific dew point temperature governed by thermodynamics. It is important, especially when we are trying to best deal or manage SRU turndown conditions, that we have operational alignment with the recommendations that flow from a formal SRU performance evaluation. Dew point temperature will fluctuate. It will increase or decrease relative to the extent of the Claus reaction that is taking place in each bed. In the condition of SRU turndown, we overall have less H2S and SO2 in our system. As a result, dew point temperatures will be reduced in our system. When we are on site, not all, but there seems to be many facilities, for whatever reason, seem to operate their reactors, at least downstream of the first converter, hot, on the hot side, and that does not best promote the Claus reaction. Process measurement and control. Accuracy of flow measurements. We've had a significant change in H2S concentration or feed flows relative to what our facility was designed with. Well, you know, what is the applicability of original orifice plate specs in terms of accurate flow measurements? Valve response and tuning parameters. You know, if there's any operators on here, they typically like to operate valves within 30 to 40 to 80% opening. That's where they like to run. This is a very interesting picture here. It is a little blurry. This was a cutout from a screenshot at a facility that we visited in the summer that it is experiencing very severe turndown. We see on the left here clean acid gas. We follow our flows. We have a temperature of 114 F. We have a flow of 0.01 mm standard cubic feet per day. The stream coming up here. I had to cut this off. The operator didn't want anything on here that could show exactly where the facility is at. But anyway, the 0.29 is it's a refinery at sour water acid gas flow. So heading from our amine unit, we have 0.01 mm SCF per day. If we follow this along, a portion of that flow goes to the front towards our reaction furnace. We further it along. We take slipstreams because we have direct fired reheaters at this refinery. So apparently we're coming in at 0.01 mmFC per day, and then further along somehow we're able to generate 0.03 mm of that same stream and also 0.04. Because of high turndown, the orifice plates are no longer properly sized for the flows that this facility is experiencing. As a result, they do not have accurate flow measurements of primarily their acid gas feed stream coming to the SRU. So if we can't accurately measure the amount of amine acid gas coming to our SRU, how can we add an appropriate amount of air to our system to ensure that we have a 2-to-1 H2S to SO2 ratio everywhere downstream in our system? it's essentially impossible. What this means is that you're running blind. This facility will have to shut down, and I believe they have to change out their orifice plates to have more accurate flow measurements. What else can we do? We can create dynamic models of our SRU. We can create a complete offline virtual SRU to evaluate some of the following. The effect on operations or performance due to a significant change in feed composition or flows. Process bottlenecks. We can also formally evaluate individual unit capability or processing capacity. We'll look at individual condensers, catalytic reactors, the reaction furnace, things like this. We can also evaluate proposed equipment modifications. It's a very powerful model where we're able to incorporate detailed equipment information and all of your control strategies. We can input your current logic and algorithms, specific valve data and blower curves, and we're able to assess changes to our process. And as a result, creating dynamic models with VMG Sim Dynamics to be able to evaluate certain process changes, it really is a tremendous training tool for you and your team. Just a few slides to end off on VMG Sim Dynamics. Other challenges that we can experience due to turndown conditions is issues with original combustion air blower performance and surge studies. You can imagine if we are processing less acid gas, there is a change to the unit's overall air demand and pressure profile in our system. If we're operating at a point that's so low, is that blower now surging? From a control and reliability standpoint, we don't want that to be our new operating point under these new operating regimes or turndown conditions. Control scheme evaluation. This particular SRU, I believe this was another project in the Middle East. This particular SRU, for whatever reason, had two main air valves in parallel. So were they both necessary now under turndown conditions? Important question. The answer was no. This facility was going to remove one air valve and we're going to have control through only one line. And basically, we're able to assess the sensitivity and response of existing equipment and control strategies right here in our live offline virtual plant with VMG Sim Dynamics. We have controllers set up for our main air. You see a control valve. We have our trim air. We have a control valve and controller. We have controllers on our acid gas flow, sour water flow in the bottom. A very, very, very powerful tool. And essentially power, if you would, is directly proportional, or the fidelity of the model is directly proportional to the amount of information and data that can be provided to us to create the model. Again, there's a control layer. We can input detailed equipment information. The power and potential of the model is directly proportional to what can be inputted. Finally, tuning parameters. We can fine-tune existing or determine new set points for a change in SRU operating conditions. Several different examples here. I believe in the middle we have an acid gas flow controller, and we have PVs and operating points. I am definitely not our team simulation expert, but it's an extremely powerful model, and we're able to assess performance at a wide variety of different capacities, and it's very, very easy. And the model can have a very high fidelity with the level of equipment information, and also formal performance testing results can be inputted to fine-tune the performance of things like our catalytic converters or reactors, and we're able to evaluate projected performance under new conditions, and any change that we may need to make with respect to our control schemes. With that, a few final remarks. Again, the need for optimized sulfur recovery unit operations. Again, emissions and environmental regulations are only becoming more stringent. As a result, the SRU is a very important unit, but it's potentially challenging as we attempt to best manage turndown conditions. You know, it seems like everything that we talked about, either a high efficiency burner or oxygen enrichment or fuel gas co-firing, it seems like everything will negatively impact your bottom line in terms of operating costs and or capital requirements. But remember, that's just for the SRU. The important takeaway today is that sulfur emissions compliance, achieving our required levels of sulfur recovery, that's our insurance for the entire facility. That ensures that our moneymakers upstream will continue to be running 24/7, we hope, day by day by day. So with that being said, highly recommended to be proactive by way of regularly scheduled performance evaluations to understand, where am I at? I mean, let's trend it out. Is my feed quality or flows, are they increasing with time? Are they decreasing with time? And also what we just showed with VMG Sim, the ability to self-evaluate future operational projection is extremely invaluable. With that, I will conclude. Thank you for attending. For more information, please visit our website, which is listed, www.sulfurrecovery.com. And you'll notice on our website that you can register for our free quarterly newsletter if you're not already signed up. With that being said, there are a few questions listed here for me in the question panel. On your dashboard, there are both chat box options and question pop-ups. Feel free now to type in any questions. Once I deal with all of those, I will then unmute everyone, and you can formally ask me a question if you'd like. Okay, the first question that I have is, are temperatures measured across the catalyst beds? Are temperatures measured across the catalyst beds? Yes. It is very important to measure temperature across the catalyst bed. For example, we want to have thermocouples at the top layers, in the middle, and at the bottom. The Claus reaction itself is exothermic. It generates heat. As a result, we expect to see a temperature rise across our bed relative to the temperature, the incoming temperature to each converter bed. The more temperature rise, the more reaction that we can assume is taking place in our bed. Also, it's important with proper temperature measurement in our catalyst beds. We will be able to assess where is our maximum temperature in the bed. Is it at the top? Is it at the middle? Or is it at the bottom? And by doing so, we can get a pretty good idea of how old or how far along is our catalyst. Brand new catalyst, for example, because it's so new and so active, we will typically be able to see all of our temperature rise, or more specifically, we reach our equilibrium temperature at our top layers. So yes, again, very important to be able to measure temperatures across our catalyst beds. At a minimum, we recommend temperature indication at the top layers, middle layers, and bottom layers. The next question. Can this model be used for thermal incinerator optimization? Yes, absolutely. We do modeling in VMG for thermal incinerators or thermal oxidizers. We find here in Alberta that a lot of existing permits with respect to SO2 emissions and thermal incinerators are expiring. We've done a little bit of work here in the fall at some plants in Alberta to work with them to optimize thermal incinerator optimization, and we do find that operations of these are quite conservative, and there are huge, and I will call them easy, opportunities to enhance or optimize their performance, especially associated with the reduction of greenhouse gas emissions, so CO2. Are demo units available for the Ministry of the Environment? I can definitely, we can take this conversation offline, and I can direct you to people who would be able to formally answer those questions for you. I would like to contact you afterwards. Okay, we'll do that. Absolutely. Can we have a link of the webinar at the end for those who missed to attend today? Absolutely. After the presentation, the webinars are uploaded to our website. So any friends or colleagues that missed the session today, have them check out our website and fill out the request to receive a link to today's webinar. And, this is the 4th webinar we've done this past year. And if any of the other webinars interest you or your colleagues, I mean, feel free to check out our website. And we've done a webinar on actually dynamic modeling of SRUs, also best practice operations with respect to Claus Condensers and also Claus converters. So some of those may interest you. You fill out a simple form, and I'll gladly send the link for you guys to download any webinar. Ooh, my favorite question. What is the average operating life of a brand new catalyst? No one SRU or facility is the same. There are different rates or sulfur inlets to process, for example. Different acid gas streams could contain a large amount of contaminants relative to other facilities or feed streams. What is the average operating life of a brand new catalyst? To best answer that question, with good quality feed streams and relatively steady, stable operations, at a minimum, at a minimum, it is expected that our catalyst will last between turnarounds. Typically, most facilities anywhere 4 to 5 years. Sometimes facilities that require enhanced sulfur recovery. For example, a lot of the refineries in the U.S. around the Gulf Coast require 99.9% sulfur recovery. They need an additional tail gas unit at the back end of the plant. As we move further down the line, those catalyst beds become more protected. And as a result, we've seen some of these downstream catalysts last north of 10 years. Can the catalysts be regenerated, or do they have to be replaced? To best answer that question, it's a function of what has caused the deactivation. For example, if we have the BTEX components in our feed streams and we aren't able to completely destroy them in a reaction furnace, they break through the reaction furnace and headed towards the first reactor. BTEX poisoning is a permanent form of catalyst deactivation. If we have poisoning due to BTEX, that catalyst, we would have to shut down and replace the catalyst. There are other times where the deactivation is not permanent. There are examples of sulfation. Sulfation can form with an ingress of oxygen through our system. We are able to do things online to regenerate and or revitalize the bed. Again, thank you for all these questions. If we need to pick up, we need to add more or pick up on this. Once I'm done formally answering all these questions that are written out, I will unmute everyone and we can have a big talk if you'd like. Are you aware of cases where both SO2 and H2S are measured in incinerator stacks? Okay, so this gets into the case of final emissions. So from our SRU, a given level of performance or sulfur recovery and everything else travels towards our incinerator stack and is burnt or oxidized to SO2. I'm trying to think with my various site visits if I can think of an analyzer on our incinerator stack which also measured H2S. I don't think that I've seen it. I don't think that I've seen it. I will say this, depending on what country that we are working in, some places won't even have an SO2 analyzer on their stack, unfortunately. It's true. A lot of places will have just an SO2 analyzer, but the best practice operation is a mass-based analyzing system where we measure SO2 emissions and also the mass flow rate through our stack. And if we're able to measure mass flow through our incinerator stack, we can optimize the amount of combustion air that we add to our stack. And through that, we're able to minimize our overall CO2 or greenhouse gas emissions. I have another question here that I'm not sure if I understand, so we might have to pick it up. We might have to pick it up after the webinar. Dump-in zone modeling of reaction furnace in VMG. I believe that may deal with how we specifically or where we specifically introduce the feed streams to our SRU into the reaction furnace. For example, does all of our feed go through the front? Do we process all our acid gas through our main burner, or do we bypass a portion or slipstream around the main burner and drop it into the second zone of our reaction furnace? We can pick this up after, but yes, if I read the question correctly, we are able to model split flow introduction of acid gas feed streams to our reaction furnace. That the setup of that model is not, there are a couple additional steps involved if we wanted to do something like that, but no, definitely done when we are on site and we're working at refineries which do operate their reaction furnace in a split flow fashion. Okay, contact info. Can the model estimate and track catalyst activity? So a lot of questions about dynamic modeling and its capabilities. We're going to leave some of this discussion to outside of the webinar, but definitely can provide a lot more information and examples about what we've done in some of our projects for our clients with respect to dynamic modeling of SRUs. Are there resources available on various types of shutdown and startups of the SRU plants? Yes, there are resources. SRE is a tremendous resource. Startup and shutdowns of SRUs is one of our core service offerings. The guys are actually headed out most likely on Sunday down to the US to help a refinery in Salt Lake start up their SRU. They just changed out their catalyst. They want to start it up and make sure that they have a safe and reliable startup such that once they switch back to acid gas, there are no issues. This is also something that we can pick up offline. And also, once we close the webinar today, there'll be 3 very easy questions. And one of them is, what topic would you like to see covered in our next webinar? And I believe one of the potential answers is the startup and shutdown of SRUs. Are there cause and effects tables available? I assume that's tied in with the startup and shutdown of SRUs. Shutdowns and startups of SRUs are very important. They're also very difficult. Part of the problem is that in general, SRUs run quite steady between turnaround periods. So as a result, shutdowns and startups become quite special activities where our team maybe doesn't have a lot of knowledge in the proper procedures because they haven't done them before. Proper startup or shutdown involves burning fuel gas such that we on a shutdown can have high mass flow through our plant and melt out any sulfur that has inevitably set up in our process. And on a startup, we burn fuel gas in advance of introducing acid gas to get our bed temperatures and process up to appropriate temperatures. We burn fuel gas, we add oxygen. It's important that we don't add too much oxygen or excess oxygen because that could react with sulfur in our system. We could have sulfur fires. Oxygen plus sulfur yields SO2. That reaction is also very exothermic, yielding a sulfur fire. If we don't add enough oxygen when we're burning fuel gas on startup and or shutdowns, we could start cracking the hydrocarbons or methane, if you would, in our fuel gas, and we could start forming soot. Soot will set up on our first reactor. When we go back or switch back over to acid gas, we're going to have a high pressure drop or DP across that first reactor. In the absolute worst cases, we're going to be trying to come out of a shutdown with a nice startup, and we're going to have to shut back down again to skim off this soot that's formed on top of our first reactor. Best practices to measure and track conversion and recovery as well as incinerator combustion. Well, formal SRU performance testing is required to formally measure interstage conversions. So, the chemical reactions that are taking place across reactor 1 and across reactor 2, for example, in a 3-stage SRU, requires formal on-site analytical testing to understand what's going on under the hood inside my process. If we have accurate flow metering or measurements on our SRU feed streams, and we have a final SO2 analyzer that's reading accurately on our stack, we're going to be able to have what we hope is a fairly accurate calculation of daily sulfur recovery. But what we don't have is how is the interstage catalyst performing, and with that we need formal performance evaluations or testing. Best practices is to have on-site performance testing conducted twice per year. At a minimum, you'd want to have an assessment conducted on an annual basis. And that way we're able to measure and track conversion and recovery over time. And and also, compare our results to what the specific facility themselves are calculating. And at times there are discrepancies, unfortunately. Is there a phone number that I can contact you after the webinar? Absolutely. We'll get that sorted out here after. Just don't go anywhere. I'm going to unmute everyone here shortly, and we can get everything squared away to have set up a call after this. Are you aware of a typical refinery fuel gas processing and online measurement of sulfur species in fuel gas? I don't believe that I've seen an online measurement or online analyzer for sulfur species in fuel gas. With respect to fuel gas, if we decide that due to turndown conditions, we need to and want to co-fire with fuel gas in our reaction furnace, we recommend that we use a purchased or city fuel gas stream. That way, typically what we see is that stream consists of typically north of 93% methane. There will be a little bit of CO2. Typically in our experiences with these streams, there's very, very trace amounts of H2S. Pretty tight windows of opportunity, if you would, with respect to the generation of a purchased or city fuel gas. What you don't want to do if you're actually at a refinery where you can generate a refinery fuel gas is that you do not want to be using that stream to introduce to your reaction furnace, because that stream the quality of that stream is directly tied to the operation of your amine unit, which could be influenced by the different gases that it receives from the various operating units upstream in the refinery. The refinery fuel gas stream, there's one, for example, in the US, a regular client that I visit, they have about 30% hydrogen in that fuel gas stream, which is fine, but it fluctuates due to operating upsets and challenges upstream. As a result, we want to have a nice, steady, consistent fuel gas flow and quality, if you would, if we do want to co-fire at our reaction furnace with a city or purchased fuel gas relative to some type of fuel gas that's generated in a refinery. Can the model predict concentrations of TRS species in the incinerator? We have a model that predicts, so TRS, so total reduced sulfur. The purpose of our thermal oxidizer or incinerator is to effectively convert all sulfur-bearing species from our SRU to SO2 and have a nice, efficient, effective plume dispersion of release of our emissions, or SO2, um, um, to the environment. So TRS is total reduced sulfur. So things like H2S, COS, CS2, and also sulfur vapor. So the question is there a model to predict the amount of these species left at the outlet of our incinerator? We have a model that we utilize to predict TRS concentrations in incinerator flue gas. I was actually just using it 2 weeks ago for a client. That model itself is a standalone model, proprietary to SRE. We have not begun to work that into VMG. The VMG sulfur package was initially created based on 15 to 20 years of our SRU field testing results. It's a very powerful model, and it's been a very, very good partnership thus far with VMG. So that's something else we can talk about, is the modeling of TRS incinerator flue gas. Oh, wow, look at all the questions. Do you have a list of best practice analyzers for SRU? Okay. We're going to pick up a lot of this. After. So please do not leave. Do not leave, and we'll connect for a call hereafter. Okay, that is the end of all the questions in the question tab, and thank you so much for asking so many questions. Really, I find that a lot of the major value is extracted at the end when we can talk about your own issues or concerns, operating questions, challenges, etc. But it doesn't have to stop now. What I'm going to do is I'm quickly going to unmute a few of the attendees that we have left, and we can formally ask me some questions. In the chat box, what I'm going to do is I'm going to write my email again for you. .com. I hope you can see that, and I'm also going to leave my cell phone number. So if there are any questions that you may have, or things that maybe tomorrow you'll wake up and think of something you forgot to ask, feel free to send me an email. Or also, I left my phone number here. I think, yes, I did leave my phone number. You can call my cell phone at any time. That being said, I'm going to unmute 3 of you that are remaining. And if you do have any questions, please feel free to just formally ask me. I think Mr. Sharifi would like to have a phone call after this. And Mr. Anwar was asking about the modeling of reaction furnaces and temperatures. I'm not sure if I properly answered that question for you.
We can talk on this one-on-one sometimes later. This was
someone's talking. Is that Mr. Sharifi? Mr. Sharifi, I left my phone number and email in the chat box, so feel free to give me a call or write me a message after the webinar. Just please give me a few minutes to get resettled. I need some water. I've been doing lots of talking, but it's been very good. Thank you for your attendance today. I hope that you found the session valuable and informative. With that being said, I'd like to thank all of you for attending, and upon leaving, you'll see a survey that we would greatly appreciate you filling out. Very, very easy. And with that being said, thank you. Have an excellent day, and thank you very much.